Hello everyone, my name is Howard Nguyen, and today I'll be doing a radical halogenation of alkanes mechanism. This is some of the directions for the problem. So we're going to predict monohalogenated products, and we're going to show the mechanism using fish hooks to show like the electron flow that leads to our product. And then we're going to include stereochemistry if necessary for each of our products. And then after we finish the problem, we have to answer this conceptual question. If this were bromination, where would bromine attach? So let's jump right into it with this reaction. So in this reaction, we have a tert-butyl cyclobutane, and it's undergoing chlorination. And what we know about chlorination is that it's not very selective. We're going to have multiple products. What I'd like to do first with this problem is I want to list out all the hydrogens on the different carbons and see if there are any common hydrogens. And one way we can tell if there are common hydrogens is if there's an internal plane of symmetry within our structure. And there is, fortunately. Let me draw it. We have this internal line of symmetry. Another way we can actually check if our hydrogens are the same is by nomenclature and naming. So, okay, so let me grab out a couple colored pens. If you guys have a couple other colored pens, it might be helpful in listing out like if there are the same hydrogens or different hydrogens. Okay, so with this internal plane of symmetry, we know that these hydrogens are the same. So as I was saying, we can use nomenclature as well to see that these hydrogen groups are the same. So let's say our chlorine attaches to this hydrogen group. What would we name it? We would name it 1-tert-butyl 2-chlorocyclobutane. If we attached it here, what would it be named? The same exact thing. It would also be 1-tert-butyl 2-chlorocyclobutane as well. Therefore, these two groups of hydrogens are actually the same. And then the rest are actually all different. So you guys have different colors. It might be helpful. All right. Okay, this one's faint. I'm going to actually use a different one. All right. This one. All right. And then we also have this one. And then on the tips, the terbutyl for all of these, we're gonna get a bunch of hydrogens as well. I'm not gonna write them all out because there's very little space in here, but yeah, just know like on the tips of the terbutyl for like the CH3s, they're all different. They're all the same. They're all the same, sorry, hydrogen groups. So the first step of tackling this mechanism is the step of initiation. That's when we have a non-radical species and we're going to form radical species. We're going to form it through homolytic cleavage. So here we have chlorine binding to another chlorine. And with homolytic cleavage, we're going to break their bond. Now we form two radical chlorines. And just know, like, you can abbreviate it like I did to two radical chlorines, or you can actually draw out the two radical species. The next step is propagation. Propagation is actually one of the most crucial steps because it's what leads us to our product. With this problem, within propagation, there's actually two different steps. The first step is something called a hydrogen abstraction, and then the second step is called the halogen abstraction. So with a hydrogen abstraction, basically, we take one of these groups of hydrogens, one of these hydrogens and one of these groups, and basically what we're going to do is we're going to try to form a radical. And we do that by actually binding it to one of these chlorine radical species we just made an initiation. So we're going to have this chlorine radical right here. And then let's say we start off with a hydrogen on one of those CH3s, all right, on the terbutyl, all right? And I'm gonna form a radical right here, breaking up the bond. So I'm just gonna be like right here, and then this one right here. All right, that leads us to forming a radical right here. We formed a radical right here. All right, the next step is a halogen abstraction. And this is where we actually form for our intermediate. All right, which leads to our product. So for this one, basically what we want to do is we're gonna take a non-radical species. All right. We're gonna take a non-radical species, we're gonna make them into a radical. All right. And then taking one of these chlorines, we're gonna actually form a bond with our radical. And it leads us to our first intermediate. Voila, our first intermediate. Now we'll decide if it's actually the product after we determine if there's stereochemistry involved, but I'll do that at the very end. I just want to get each of the intermediates. All right, so same thing. We're gonna do a hydrogen abstraction. So let's do this hydrogen right here. All right, basically, I'm gonna take this hydrogen. I'm gonna break it apart. Actually, I meant to actually break it over here. We're gonna have that radical chlorine. It's gonna bind to, all right, making our radical. And then we're gonna have that chlorine bind to another chlorine. All right. We're gonna break it apart. And then we're gonna have to form a bond. And once they're radicals, we're gonna form a bond with the other radical, leading to our second intermediate. And chlorine. Here, our second intermediate. All right. And it's just the same steps for each of these for the next two as well. So let's do hydrogen right here. All right. We're gonna a radical right here. And I'm actually going to draw the chlorine. Draw right here. All right. Then we get a radical right here. All right. And then have our chlorine right here. All right. We're going to break it apart, form radical species. All right. I'm going to type it from actually down here. All right. And it leads to our next product. Sorry, it might get a little messy because I'm writing it actually closer to the ground now. All right, and you get chlorine, and then, all right. And then our last intermediate, which is the hydrogen down here from there. Okay, so our last intermediate, have this chlorine. All right. We're gonna break here. Okay. And then this one. All right. Right there. All right. Break these. All right. And then we form our last intermediate right here. And then right there. All right, to recap, propagation, we did a hydrogen abstraction to get a radical, and then we did a halogen abstraction to actually put on a chlorine and attach it to the radical group. So we have our four intermediates. Now, we got to determine if they're stereochemistry or not. All right, so looking at this, of course, there's not going to be stereochemistry here because the chlorine is just attached to a carbon like outside. It's basically like almost primary. Here it's attached to a tertiary. But because there's it's disubstituted on carbon, it won't form any stereochemistry. Now these two are the special cases of disubstituted alkanes. So disubstituted alkanes, they're known for forming cis and trans products. So let's draw that actually. With cis products, we're gonna get both bold lines, and for trans products, there's gonna be one dash and one bold. And to be honest, like we're only gonna be changing the chlorine from bold to dash and dash. And there's a reason for that, which I'll explain in a minute. But let's just draw the stereochemistry for these guys. So draw the bold and then the dash. Sorry, you guys can see that. And the dash. Then there's a dash. All right. And then same thing for this one. It's gonna be a bold. So bold on both sides. And then the chlorine I actually turn into dash. All right. Now you might be wondering, why is it only the chlorine that's changing from bold to dash? The reason is what kind of hybridization are radicals again? They're sp2, that's right. sp2 are trigonal planar, and that means they're flat. So that means the chlorine can attack from that has the equal chance of attack from the top and the bottom. Therefore, chlorine's the only one that's changing. Also, chlorine's the only one that's being reacted, not the tert-butyl. Therefore, it's only the chlorine that's changing from bold to dash. And also, these make diastereomers. All right, and the last step is termination, and that's when we have two radical species, and basically they're going to bond together to form a non-radical. They form a non-radical. And that basically sums up all of our products. So overall, we have 6 products. We got 6 products. Now, we have to go back to the question of if this were bromination, where would bromine attach? Well, to answer this question, we actually have to go back and look at something called, we have to go back and look at something called free radical stability trend. This talks about how when a radical forms, it will form a tertiary, secondary, primary, or on a methyl. It's basically tertiary, it's attached to 3 different carbon groups, and then 2 carbon, and then secondary is 2, and primary is 1, and then methyl, it's not really that many carbon groups. It's not like on it like bonded to many carbon groups. The thing with bromination is that it's very selective of where it wants to be. So it wants to basically like attach itself to the radical with the greatest stability. So if we look back at our structure, we look back at the structure of our problem. All right, if we look back, okay, to the structure of our problem, where do you think it would attach itself? If a radical to be formed from any one of these H's, where do you think it would attach itself? Well, wouldn't be here because it would be primary. So these H's are no good. And all of these guys out here, they're only secondary. So those are also no good. Therefore, there's only one option, that one. It's tertiary. Therefore, if this were a bromination problem, it would attach there because bromine is a very slow reaction, so it's very selective, and it will select the radical stability, the greatest radical stability, which would be tertiary. All right. Thank you so much, everyone, for listening. I hope this uh, help everyone gain better understanding of the mechanism of radical halogenation of alkanes. And I hope everyone has a great night.